Alright, this time let's do it quantitatively using mathematics. And of course, we are following exactly the same procedure. So there we divided the slit into n zones of equal width delta y. And then originally we said the width of the slit was a. So therefore, simply a is equal to n multiplied by delta y. And then in the previous slide, we also learned that if you are at an angle theta away from the central position, then the phase difference between the two light waves coming from adjacent zones like this could be written this way. Okay. And then here, let's think about another thing. Now we have divided the slit into n zones, and what will be the phase difference between two light waves, one from the top zone and the other from the bottom zone, between this and that? What will be that? And well, it's not very difficult. Actually, this phase difference was equal whether you are here or there or here. They were all the same. So therefore, the phase difference between this wave, the first wave, and then the last wave was simply n times the phase difference given here. So therefore, let's call it phi. It will be the n times the phase difference that we found above here. And then we know that n delta y is equal to a. Okay, now we have it ready. And then think about the actual size of the amplitude and the intensity. Okay, this is what I have already explained verbally. So if you are at an angle 0, all the phasors are pointing along the same direction. So therefore, their combination makes a full large amplitude, which we call EM. Okay, this is the maximum amplitude, and then of course in that case the maximum intensity will of course be square of the maximum amplitude, right? Okay, and then how about at angle theta? So in this case, the now angle between these phasors, for example, will be the delta phi, and then we learned that they form an arc. And then what is the phase angle difference between this phasor, first one, and this phasor, the last one? Of course, this one corresponds to the phasor here, and that one corresponds to the phasor here. And we learned that their phase difference is given like this. So therefore, if you draw a line like this angle will become phi, which is given here. Okay. And then because these form an arc, now actually the amplitude we want to know is this guy here, this guy. And in order to figure it out, let's try to draw the lines for the radius of this arc, which is just like this. And then we know the relationship between the length of the arc and the angle and the radius, which is just like this. The length of the arc is equal to radius multiplied by the angle of the arc, right? So following this relation, now we can say that phi is equal to EM divided by R. Why? Actually, this angle is equal to this angle. Why? Because this radius, this line, is perpendicular to this. This is 90 degrees. And this line is also perpendicular to this. So therefore, if you can simply figure out that according to the geometry of this, now this angle becomes equal to that. Okay. So therefore, now we have this relation. But like I said, what we want to know is the length of this guy, right? Okay. So if you again draw a line like this, then you form a triangle, and this angle is half of phi, and this length is half of amplitude. So therefore, from here, we know that the amplitude at the angle theta is actually 2 times of the r, which is here, multiplied by sine of half of phi. Okay, so we can write it this way. And then here, let's try to use this guy and then put it in here, and then this is what you get. Right. Okay, now in this case, okay, it looks a little bit complicated, so let's replace half of phi with alpha. Then we can rewrite so that we can write it this way: em multiplied by sine alpha divided by alpha. Okay, we can write it this way. So this is the angular dependence of the amplitude. So therefore, we can finally write the intensity like this. Now the intensity is of course the square of the amplitude. So therefore, this square of the amplitude now becomes square of the sine alpha divided by alpha. This is the angular dependence of the intensity. Okay, and what is alpha? Again, alpha is half of phi, and of course it can be again written based on sine theta, right? Okay, and then what we finally have to figure out is that what kind of function is this? Now this function, in the upper part we have sine square. So sine square changes from 0 to 1, right? So it moves like just sine square like this. So therefore bottom part is 0 and upper part is 1. But at the same time it is divided by alpha square. So alpha will keep increasing as we go away from the center, right? And then if the denominator is increasing, the result will become smaller. So therefore it explains why everything becomes smaller if you move away from the center, but at the same time from time to time you come across dark bands. So this is the position of the first dark band, which is here, and this is the position of the second dark band, which is here. So condition for the dark band was written like a sine theta was equal to m lambda, but except 0. So on the 0 corresponds to the central position, so this is not a dark band, right? Okay, now this explains the quantitative results of the single slit diffraction intensity. Okay, so here we will go one more step and think about what will be the diffraction intensity from double slit but with wide opening. Okay, this is different from the Young's double slit experiment, because in Young's double slit case we considered narrow slits. And what do we mean by the narrow slit? Narrow slit actually means the size of the opening is much smaller than the wavelength of the light. Okay, in this case we can effectively say only one streak of light pass through the slit. Okay, and of course in Young's double slit case we only had to consider therefore the interference between two light rays, so it was much simpler. Okay, anyway, in order to understand the diffraction of the double wide slit, let's do it step by step. We will first consider the case of the double narrow slit, and then also consider the case of the single wide slit, which we already have learned, and then finally try to figure out the case of double wide slit. Okay, first, the Young's double slit experiments. Let me remind you that in that case the intensity was just like this, cosine square of the beta, and beta is proportional to the sine theta. Okay, and then again, can you remember what was the condition for the constructive interference? In double slit case, if the d is the distance between two slits, then d sine theta equals to n lambda. This was the condition for the constructive interference. So therefore, in this graph of the intensity, the central part here corresponds to n equals 0. This was 1, this was 2, and this was 3, and so on. Okay, and then therefore the interval between these two bright bands can be written like this in terms of angle theta. And another important thing I have to remind you is that now cosine square always changes between 0 and 1. So even when you move away from the center, intensity remained strong. Okay. And then now the second part, let's try to remember what we learned about the single wide slit. Okay, in that case, single wide slit of opening A, so it is wide, so which means that it is larger than the wavelength. This is what we learned in the last slide. So intensity looks like square of sine alpha divided by alpha, and alpha was proportional to sine theta, and also this part includes A instead of D, right? Okay, and we learned that in this case the constructive interference condition doesn't really exist, but the destructive interference can be written like A sine theta equals to m lambda, and m cannot be 0 because 0 corresponds to here, and this is the brightest band, but here the dark band is 1, 2, so m are integers without 0. Okay, and then in the denominator we have alpha, so therefore as alpha increases the overall profile becomes smaller, right? Okay, this is what we learned. So finally, now based on these, let's try to think about the case of the double wide slit. If you have a double wide slit like this, let's say the distance between the two slits is D, and then each slit has the opening size A, then what will be the intensity from the diffraction here? You know, and now two slits have wide openings, so each of them will produce a very wide area of wavefront. So mathematics may be very difficult, but in fact it is surprisingly easy and simple. So what I can tell you is that the intensity of the diffraction coming from this double wide slit is simply a product between the intensity of this double narrow slit multiplied by the intensity of the single wide slit, and the result looks like this. Okay, so in mathematics it is simply a multiplication between cosine square beta, which is coming from the double narrow slit, and square of the sine alpha divided by alpha, which comes from the single wide slit. And you know, when you multiply two numbers, whenever one of them becomes 0, the result will also be 0. So therefore, for example, here this curve becomes 0 over here at many places, and at the same time, as a result, this also becomes 0 at the same positions. And then this single wide slit case, there is a first minimum, a second minimum. So therefore, in the double wide slit case, also there is a very wide first minimum and a very wide second minimum. Looks the same, right? Okay, so therefore the intensity result of the double wide slit contains two information. First, the overall profile. Overall profile gives you the idea of the size of the opening, which is A. So this interval here is determined by A, and also if you look at it closely, the interval between these bright peaks, these bright peaks is determined by the distance between two slits, so therefore it is determined by D. And if you look at this graph, if you look at this figure, and of course D must always be larger than A, right? A cannot be larger than D, so therefore 1 over D is smaller than 1 over A. So therefore here it is naturally true that this interval must be smaller than this interval. It makes sense, right? Okay, so as a summary, I can tell you that the intensity of the diffraction coming from double wide slit is simply a multiplication between the intensity of the double narrow slit and intensity of the single wide slit. Okay.